Hello, this is Dr. Michael Hassan, the engineering doctor, and this is lecture number 7, Logic Gates and Boolean Algebra, Solved Problems. We will solve a number of problems here. This is for the course titled Digital Logic Design or Digital Systems or Digital Electronics. The next slide is a disclaimer for you to read. There are many references in digital logic design. Few examples are listed here. Problem number 1. We are given the expression f of x, y, and z equals to x prime y of x, y, z. We'd like to determine the canonical sum products form for f. Also, this is known as the sum of minterms. There are two ways to solve this problem. The first way is to generate the truth table, constitute the truth table for the function. Then for every value of the function 1, we'll look at the corresponding midterm. Then by adding all the midterms, we'll represent the function f. Or we can use Boolean Algebra. To do that, we will look at every term and we study it. We have the first term is x prime, the second term is x prime y, and the third term is x, y, z. So x, y, z has 3 variables, and this is the midterm 7, so we don't need any expansion. However, x prime needs 2 switching variables, y and z, and x prime y needs the switching variable z. How we add those variables? To add those variables based on Boolean algebra, we have x prime equal to x prime and 1, and the 1 is equal to y or y prime, z or z prime. So by doing this, we can say x prime and y or y prime and z or z prime is related to x prime. So we expand it here, and then we'll multiply to generate all midterms. The same thing with x prime y. Expand, we add, multiply it by z or z prime, which is also 1, or x, y, z, which needs no expansion. So we multiply n. This is what x prime, x prime, y, multiplied by z or z prime, and x prime, y, z prime, x prime, y, z, or x, y, z. We'll multiply again here. So we'll end up with this formula, x prime, y prime, z prime, which is midterm 0, x prime, y prime, z, which is midterm 1, x prime, y, z prime, which is midterm 2, x prime, y, z, which is midterm 3, and x, y, z, which is midterm 7. And this is what the sum of midterm 0, 1, 2, 3, 7. Problem number 2. Would like to find the canonical product of some form for the function as x, y, or z prime. So this is, we are looking for the function to be represented as a product of max terms. So the function f as the function of x, y, and z will be x or y or z prime. Again, we will apply a simple distributive law here. We know that x or 0 is equals to x, so we can add zeros as much as we want. And y prime is equals to 0, z prime is equals to 0, so we can expand x to 3 variable. Okay, by doing that, then the same thing with y or z prime, we can add 0, which is x or x prime, because we have this variable is missing. Then we will use distributive law to expand on this. This will be x, y prime, z, x or y prime or z prime, then x or z prime or x, y or z prime or x, y or z prime or x prime. And by doing that, we can rearrange the variable order. They have to be in x, y, z, so the function will look like this. X, y, z, or x, y prime, or z, or x, or y, or z prime, x, y prime, z prime, x prime, y, or z prime, which is equal to the max term 0 times max term 1, and 2, 3, and 5, for the product of capital M0, 2, 3, and 5. Again, here we use simple Boolean algebra to expand the function to product of max terms. We would like to find the canonical product of some from function x prime y prime z prime, x prime y prime z, x prime y z prime, or x prime y z. The function given as the sum of the midterms 0 to 3. So therefore, f prime will be the sum of the remaining midterm from 4 to 7. F, which is f double prime, which is the complement of the sum of midterm 4 to 7. And by using De Morgan, this is the product term of max term 4 to 7. Or simply will be equal f will be x prime y of z, x prime y of z prime, x prime y prime of z, x prime of y prime of z prime. Problem number 4, we would like to implement the following logic gates with all NAND gates. As we said, the NAND gates is a universal gate and means any expression, any function can be implemented with NAND. Also, NOT gate is an exclusive gate. It means all the switching function can be implemented with NOT. To implement first an inverter based on Boolean algebra, x equal to x and x, and if we take the complement of this side of the equation, x prime, which is an inverter, is an AND gate, with two inputs of x. So the simple here for the inverter is an input x, the output x prime, and if the input x, the output will be corresponding x prime, which is the output of an AND gate. To implement this a buffer, if we complement the output of an inverter, it will be a buffer. So two cascaded NAND gates will be a buffer. AND gate, to implement an AND gate, okay, so simply if we have an AND gate, and we take the output to an AND gate, or inverter will get an AND gate. So we can implement an AND gate with AND gate followed by inverter AND gate. Now, an OR gate based on De Morgan, x or y complement will be x naught or y naught. Then we complement again, this is x or y will be x naught or y naught naught. It means this is an AND gate with two switching variables are inverted. So an OR gate will be not NAND, which is x, y inverted first level, then take it to another gate, give an OR gate. In E, we would like to implement an OR gate, so the output of an OR gate, okay, if we take it to an inverter, will be an OR gate, as simple as this. Exclusive OR gate from the truth table of the exclusive OR, it's equal to M1 plus M2, which is x prime y or xy prime. We can expand on this by adding 0. We can add as much as 0, so we add x prime, y prime. We factor out x and we factor out y, so we'll get this equation. We'll use De Morgan, we will get this equation. And we will apply one complement on the De Morgans. So this OR gate will be converted to an AND gate. So this is really an AND gate, and this is an AND gate, and all will be taken to an AND gate. So we need the following though. We need x and y, and the first NAND gate will give me xy naught. As you can see it, xy naught, which is it's an AND gate. So this NAND gate will be xy naught. Then this will give me x and xy naught. As you see this one here between the parentheses here. Okay, so this is give me the output here, and this is will give me y and xy naught. It's right here. And if we take those two to an AND gate, give me the output, which is the exclusive OR, x exclusive OR y. If we complement the output of this exclusive OR we get exclusive NOT. So this is quite simple. Problem number 5. We would like to convert the following expression from a non-standard form to a simplified standard sum of product form. We have A or DE, C or D prime, or E or D prime. We multiply out, we'll factor DE. When we factor DE, we'll get 1 plus C plus B prime plus D prime. Since we have 1, this is all replaced with 1, because 1 or any variable, set sum of variables will be equals to 1. So this will be DE. We have possibility for consensus theorem because I have D and D prime. Coefficient here is A, the coefficient here E. So AE can be cancelled out, and we'll end up with AC, AB prime, or AD prime, DE. So this is the final answer. Problem number 6, we would like to construct the truth table for a function AB or CD. We find the values for the function f and its complement. We like to express f as a canonical sum of product, which is sum of midterms, and we like to express f prime as a product of sum, canonical product of sum, product of max terms. To do that, we will construct the truth table, the variable, for variable ABCD. Building the truth table, we start with the least significant bit D, and we toggle 0, 0, 1, 0, 1 till the end. We have 16 rows here, and 0, 0, 1, 1, and so on and so forth. Then we calculate A and B. This is an AND operation. C and D. Take F, A, B, or C, D. Then, as you can see, we generate F1 here because I have 0 or 1 is 1, and we generate 1s here. So F will be the sum of the terms 3, 7, and 11 to 15. F prime will be the product of the max term when F prime is 0, which is 3, 7, 11 to 15. And we can find f prime as the sum. He's not asking as the sum of midterms when f prime is 1. Or we can f prime from f by using De Morgan. Because if you take f prime, which is the complement of the sum, will be a product term, and the midterm will be changed to a max term. So this is problem number 6, very nice problem. Problem number 7, we would like to simplify the following expression, xy or yz or x prime yz. Here we will factor y out, you will get x or z or x prime z prime. Since we have z or x prime z prime, this will be converted to z or x prime. Okay, we have theorem on this. Or x, y. Now x or x prime will give me 1, 1 or z will be 1. So 1 and y is y, and the output will be y. So the output independent on the two variables x and z. Problem number 8, would like to simplify the expression x prime, y prime, x prime, z prime, xy, and x prime, y prime, or z prime, all prime. We'll use De Morgan to open this parentheses here. Then we multiply n. Then what we will get, we'll get this expression, x prime, y prime, x prime, z prime, or xy. We'll multiply, this is x, y double prime, z double prime, or yz. We multiply n, we get this equation. And the interesting thing, we'll end up really with x prime or z prime or x or y prime. Now x prime or x is 1, 1 or z prime or y will be equals to 1. So the output is 1, independent on any of these switching variables. And 1 is equivalent to plus 5 volt. And we have seen a circuit before for the F1 implementation as an LC circuit, or can use a triple 5 timer to generate a stable 1 output. Problem number 9, we have given the function wx or yz. would like to implement function as AND or. Well, the function does not need simplification. It is AND gate, WX, WZ is AND gate, and taking the outputs of those AND gates to gate to implement. So I have WX, give me a WX of the output of AND gate, and give me the output F, which is WX or YZ. Now, if we use De Morgan on the function F, we will generate F prime, and F, which is will give me all NAND gate. So WX prime, WZ prime, all prime. So AND OR is equivalent to NAND. Problem number 10, given the expression F is WX or YZ, we would like to implement with NOR. To do that, we will replace WX or YZ with WX or Y, WX or Z. WX or Z, and this will be W or Y, X or Y, W or Y, X or Y distributive law, W or Z, X or Z, and we take F prime, so we will complement all these. Then we will take F, which is the complement of F prime, we use De Morgan, and here, as we can see, the AND OR replaced with all NOR. So F will be double prime. This is a NOR gate, this is a NOR gate, this is a NOR gate, all take it to a NOR gate. So the output here we have NOR gate W NOR Y prime Y, and the F will be X or Z, YZ, NOR gate implementation. Given the expression WX or YZ will find its dual and its complement. F is WX or YZ. F dual will be W or X, Y or Z. What we did here, this AND gate replaced with an OR gate, and the OR operation replaced with product with AND, and WZ is AND operation replaced with OR. So here we have the dual. Now to get the complement every variable without changing the operations. So W will become W prime, X will be X prime, Y will become Y prime, and Z will become Z prime. So we can use De Morgan on this, and we should end up with the same answer. Problem number 12. We have given a very simple function as a function of W, X, Y, and Z, which is W prime, Y prime, W, X, Y, X, Y prime, Z, W, X prime, Z prime, W, X, Y, Z prime. We'll try to look for the consensus theorem. What do we find? We find here W prime and has a coefficient Y prime, and W has a coefficient XZ. So W prime XZ or XW prime Z, which is this coefficient, is redundant, can be removed. So if I cancel this, I will end up with function W prime Y prime, WXZ, WX prime Z prime, WXYZ prime. I'll factor out WZ prime. WZ prime is here and is here. So we'll get X prime or XY. X prime or XY is X prime or Y by theorem, by law. So we'll get W prime Y prime or WXZ or WXZ prime X prime. We will multiply in, so we'll get WZ prime X prime and WZ prime Y. And this will be the final answer. W prime Y prime, WXZ, WX prime Z prime, WYZ prime. How do we know the final answer? If we can see another law or another simplification theorem can be applied on this term, we can use it. Otherwise, we stop. Don't have anything to do, any more simplification to perform. Actually, this iffy answer and any suspicion can be eliminated easily when you use K-maps, because K-map will give me a very rigid and complete answer with full satisfaction, and answer is at the best simplified form. When we come to K-map, see this is very true. Problem number 13, given the expression f, a, b, c, d, e, this is the 5 variable, given a prime c, d, or e prime f, b, c, d, I'd like to represent f as a product of sums. To do that, we'll factor out here c and d. We'll get c, d, a prime, or b, or e prime, f. So this will give me actually CD with E prime F will give me CD or E prime F. A prime or B E prime F, we have a theorem on this. CD or E prime will give me C or E prime, D or E prime. CD or F will give me C or F, D or F. A prime, B or E prime will stay the same, and A prime, B or F will stay the same, and we'll end up with a product of sums. This is not canonical form by any means, but this is the product of sum of the function f. Again, when we use K maps, we'll see we can do this stuff as well is in a very simple way. This would be the last problem, and I would like to thank you so much. Please subscribe by clicking on the logo, which is the circle with I inside it. And sincerely, Dr. Hassan. Thank you very much. This is the end of the chapter, which is chapter 2, logic gates and Boolean algebra. We may have another lecture on VHDL. I will find out. We may have another lecture on VHDL to allow us to understand how to use VHDL to simulate digital gates. I thank you so much. Bye.